couple of them.
So we make sure the slides work, I guess.
Yeah, if you want to go ahead and
Oops,
start
I need to do
sharing.
this first. Let me. Okay. You see my slides there, or do you see
Yeah.
my presenters?
Uh, no, I think we saw the slides.
Is
Hang
it
on.
still there? Is it there or not?
I gotta close my antivirus. It popped up.
Okay.
Yeah, it's still there.
Just the slides, though, not my slides and my previews.
No, just the slide.
Okay, rock and roll. You want me to leave it there or?
Yeah, that's fine. You can
Okay,
leave.
okay, rock and roll.
So how's you guys all settled in New York now?
We're getting there slowly but surely. Next week is finals week. So, it's a little busy right now, but then it'll be break and we'll hopefully unpack the last boxes that are still sitting around in corners.
There you go. I get rid of my background so that you can see what's going on in here.
Oh, I see you guys there. Yeah.
This
Where'd you
is
guys meet?
what's that?
Where do you guys meet?
Baker University, just
Okay.
south of Lawrence and KU, owns some property that and manages some other property that is all wetlands.
Okay. Yep.
And so a few years ago, they sold a little piece of the wetlands to the state so they could put a highway along the edge. And in exchange for that, the state funded this kind of cool museum. They call it a discovery center.
Neat. Yeah.
But we've been having our meetings here ever since this facility opened about half dozen years ago or so.
Yeah. Neat. The club I belong to in Chicago, north of Chicago, it's kind of the same for them. They meet at a nature center out at Volo Bog. So it was kind of the same deal out there.
Yep. Yeah. So my wife, after she saw the pictures from Bryce Canyon, she's like, "You're taking me out there next year."
Yeah. We call that Red Rock Country. It's gorgeous down there. So
Yeah, it is. It's beautiful. So did I read correctly? And I don't know if it was in the short bio you sent me or if it was maybe on your LinkedIn or something that you guys had lived in Bozeman.
yeah, I did my graduate work at Montana State. So did my wife. So yeah.
Okay, yeah, I've got a sister-in-law that lived up until about 2 months ago. She lived down in Big Sky.
Oh yeah.
We've
Okay. Yep.
been up there a lot.
Yep.
It's a big
Nothing quite
part of
like Southwest Montana.
yeah, no, it's a really pretty part of the world for
Yeah,
sure.
it's gorgeous up there. So
Yeah, she worked for a company that managed a bunch of uh, properties that where the owners, when they weren't there, they were,
ah,
renting, leasing them out.
yep,
So
yep,
she was always able to get us, these huge ski in, ski out homes on the side of the hill,
yep.
for, no more than staying at a Best Western. So
Yeah.
it was great.
Lots of those kinds of things popped up after the pandemic because folks just moved to Big Sky for the pandemic and then went back to their normal lives. So
Yeah.
yeah,
Well, I know there's a lot of, I always noticed that there were a lot of California license plates when we were up
yeah,
there.
yeah, yeah. Second homes in Big Sky is a big deal. So
But I like Bozeman too. Bozeman's kind of a cool town.
yeah, we liked Bozeman. We lived a little farther out than Bozeman. where it's a little darker. I guess these days it's not as dark as it was when I lived there, but yeah, we lived so Belgrade, which is kind of the next big
Oh,
town over.
so
We lived
yeah,
in
no,
Belgrade, so.
it's funny you mentioned Belgrade. You remember that telescope store that used to be in Belgrade?
Uh-huh, yeah. Scott Sam, yes, I knew him well.
Yeah, yeah. I bought a C8 from him many, many,
Oh,
many.
okay, yeah. Scott
Um,
was the president of our club for many years, so
it's a small world, isn't it?
yeah, yeah, that's right. So Scott's passed away now. It's sad.
Yeah,
We
that's what I heard. I heard it was
yeah,
like a beauty salon or something now.
yeah, it's something different now. Yeah, exactly. So.
No, he had it. He was holding it for. He was trying to sell it on consignment. Somebody had traded it in for a bigger telescope, and
Huh, okay.
usually if I go out of town and I know that there's a brick and mortar store that sells telescopes, I'll
Yeah,
go
you
buy
go
it.
look, right?
Absolutely, because there aren't that many of those left anymore.
No, there are not. Yeah.
And we fussed back and forth, and he got on the phone with this guy, and we negotiated back and forth, and I left with the telescope.
Nice. Well, if you do go back to Utah next summer, you should stop at the Clark Planetarium because they traditionally have had a big selection of telescope equipment in their store. You can buy eyepieces and all kinds of stuff there.
Oh,
So
okay. Is that in Salt Lake City
that's
or?
in Salt Lake, yeah. So
All right. Well, we'll give a couple more minutes and then we'll go
okay,
ahead and get started.
rock and roll.
Well, I said, and this was Jennifer who is teaching.
Okay.
Is he, yeah,
Okay.
is he the one who will come to meeting?
Yes.
Yeah,
Yeah, she's our faculty advisor.
yeah.
I was going after those.
It's really been. Anyway, I see. You need to.
So do they have a local club in Pottstown?
No, not where we are. The closest one's in Syracuse. So I think that means we're going to have to start one because, as I'm sure you know, there are amateur astronomers pocketed around everywhere. So
Right.
yeah, and it's dark up here, so we should totally do it.
Syracuse is a pretty fair haul from there, isn't it?
Yeah, it's 2.5 hours or so. I
Yeah.
went down and gave them a talk about 3 or 4 weeks ago. So, but they thought it was a long haul, but as I reminded them when I lived in Chicago, that's how long it took me to just drive across the city. So it wasn't so bad.
Yeah, well, I mean, I worked in Kansas City for a long time, but I
Oh, uh-huh. Yeah.
live about 30 miles west of Kansas City. But with the traffic in the morning and everything,
Yep.
sometimes it would take up to an hour, but I could still get to the office faster from 30 miles away than some of the people that actually lived in the city could get
Yep.
there
Yep. That's right.
because of all the traffic. So,
That's the way it goes.
yeah, yeah. All right. Well, let's go ahead and get started. And I don't want to keep Dr. Larson waiting too long. But our guest speaker tonight is Dr. Shane Larson. I met Shane this past June in Bryce Canyon for the Astronomical League AstroCon. And then we both volunteered for a concurrent event that was taking place in the national park called the Bryce Canyon Astronomy Festival. And he had his 12 and a half inch home built Dob. Is that Equinox?
That's Equinox. Yep.
Yeah. And I had my two smart telescopes, but we were there, doing public outreach for that. But Shane is a professor of physics at Clarkson University in upstate New York, and he's the director of integrated engineering and applied science project in the Wallace H. Coulter School of Engineering and Applied Sciences there. He works in the field of gravitational wave astrophysics, specializing in studies of compact stars, binary stars, and the galaxy, with both the ongoing ground-based LIGO project and the forthcoming space-based observatory, LISA. He's an award-winning teacher and a fellow in the American Physical Society. And in addition to his research and teaching, he maintains a strong public-facing science activity program. He just mentioned he had gone down to do a presentation a couple of weeks ago. And he also has a public science blog that he does regular contributions to. So, without further ado, I'm thrilled to turn the program over now to Dr. Shane Larson.
Okay, thanks, Rick. Thanks for the introduction, and certainly thanks for the invitation. Rick and I met, as he said, at AstroCon. I am a professional as well as an amateur astronomer, so I end up doing lots of talks for astronomy clubs around the country. I do them virtually a lot, like I'm doing with y'all tonight, but sometimes I travel around, and when I can and when I do, I stop and do them in person as well. So hopefully one of these days I'll come through Kansas. I drive that way usually every summer. And if not, I'll certainly see you all at some star party sometime. So the talk we're going to give tonight, Rick and I kind of went through my long list, but this is one that I like giving. It's about the Milky Way. As amateur astronomers, the Milky Way is something that we are intimately familiar with. It's one of those night sky things that we often show the public. But it's actually very core to the history of and the current work in modern astrophysics. And in particular, it's related to the work that I do in my group. So this is kind of a fun talk to give because I'm going to talk to you a little bit about the history of how we came to understand the Milky Way. And then I'll conclude with kind of the modern astrophysical research that's going on to try and understand things that we don't understand about the Milky Way. As Rick said there, I have a public science blog. So writescience.wordpress.com is my blog. I traditionally post there about once every month or so. I'm a little bit behind right now. It's the end of the semester, but over Christmas, I'll get a new post up. But there's, I don't know, 150, 160 posts there. They're about all sorts of different things. There's certainly things there about gravity and gravitational waves. There's stuff about black holes and SETI and aliens, and but also stuff about the Milky Way. So if you're interested, there's certainly stuff there to read. Hopefully, stuff that you'll find enjoyable. It is public facing, as I tell people. It's there so my mom knows what I do, and so I try and write there as often as I can. We'll certainly take time for questions tonight, and if you have any, we'll try and get them cleared away. But as always is the case, questions will occur to you later. And so when that does happen, there's my email address right there, slarson@clarkson.edu. And so please do send me an email. I'll get to it when I see it. And if you have a question that I can answer, I certainly will. But otherwise, I'll point you towards a book or a video or YouTube or something that hopefully will help you answer your questions. And if you're on social media, there's certainly my social media there. So you see in the background here, this is the Milky Way, and it is, in fact, an artist's rendition of the Milky Way. This is a view of the Milky Way that no human has ever had, and that's because the sun, which is embedded inside the Milky Way, lives down in the flat part of the disk. This spiral that you're looking at is an imagining based on real data of what the Milky Way would look like if you could stand up above it and look straight down on it. It's very flat and pancake shaped, kind of like a disk. And then it has the kind of classic spiral arms that you and I call a grand design spiral. And the sun lives out in the spur of one of these arms, about 2/3 of the way out from the center. This particular rendition has what's known as a bar across the center. This is something that has been debated for a long time, but we think now that indeed the Milky Way is a barred spiral galaxy, and we're looking at the bar from an angle of about 30 degrees, which is why it was so hard to tell for a long time whether or not it was barred or not. Those of you who are galaxy chasers, I'm certainly a galaxy chaser, that's why I have a big dob, then there are barred spirals you can see, and the Milky Way belongs to that class. Okay, so we'll talk a little bit about how we came to understand that this is the picture of the Milky Way. This is where the sun lives. But the place I want to start is here. So this is a picture of the Milky Way taken by Royce Bair, who's a very good astrophotographer in Utah. This is the Milky Way over the Grand Tetons. And as amateur astronomers, this is a view of the Milky Way that we're very used to. And in many ways, it is the view that for most of human history, humans have always had of the Milky Way, this kind of diaphanous fog of light that stretches over the sky from one side to the other. It's very prominent in the northern summer and during the northern winter, as it is right now. It's still there, but more difficult to see. So, was there a question? Sorry, I heard something. You good?
I think we're good.
Okay. So the interesting thing about that is that you and I know what this is, right? But most people today who live in cities, as we were just talking about living in Chicago or Kansas City, they've never seen the Milky Way. And very often I'll take friends out who live in the city, and some of you may have had this experience as well, and we'll go out to someplace dark and the sun will go down and the Milky Way will start coming out overhead, and then they'll give this big disappointed sigh because they're like, oh, it's going to be cloudy. We're not going to get to observe. And of course, that's not true at all. That cloud, that light that looks like a cloud as it's coming out, is in fact the Milky Way. The modern picture of the Milky Way, this is a movie that is panning completely across the Milky Way, across both the winter and summer skies. This was taken by S. Bruni and is archived at the European Southern Observatory. It is a multi-frame mosaic that was taken over the course of many years and then very diligently stitched together to give you this kind of clear view of what the Milky Way looks like stretched across the entire sky. You'll see there are some adjacent dwarf galaxies to us. This is one of the Magellanic Clouds. We'll talk about them soon. But you'll see that the Milky Way is concentrated in a very large flat disk. There are stars beyond that concentration, and as it turns out, those stars are also part of the Milky Way. Most of these are the stars that are nearby to us, and this is part of the evidence that you and I live down in the flat disk in the Milky Way, and that we're looking out through that disk. And so we see all of these foreground stars projected against the 400 billion stars that represent the Milky Way disk that we see there. Okay? Now, some of all of that I've told you, especially the numbers and the facts and the shape and the structure of the Milky Way, are things that you and I know. And it's things that amateur astronomers often know because we've kind of immersed ourselves in what our civilization knows about our place in the universe, and in particular about our place in the Milky Way. But what I want you to do is for a few minutes, I want you to forget what you know about the Milky Way and forget what you know about astronomy. To quote the great Master Jedi Yoda, I want you to unlearn what you have learned. And the reason for doing that is that I think it's very difficult sometimes as modern astronomers, as modern amateur astronomers, to kind of remember and understand how hard fought it was to earn that knowledge that we have about what the structure and shape of the Milky Way is. And it's really worth our while to remember how hard it was to learn this, because all the things that we take as the properties in the Milky Way were learned basically from right here on Earth. No human has ever traveled anywhere or around or scouted out the Milky Way. All we've learned from staying here in one place and looking out and deciding what we can learn. Okay, I often encourage people to imagine you're going to move to a new city. Imagine you could just sit on a hill and watch the city with a telescope, but you couldn't actually go walk around it. How would you learn all the things about the city that you would know? Where the streets are, how many people there are, where the grocery stores are, where to buy telescope parts, whatever, right? Imagine you could only learn that by looking at it from a telescope very, very far away. That's exactly what we've done with the Milky Way. Okay? So, the true understanding of the Milky Way really began with the very first amateur astronomer, who in fact was the first professional astronomer, and that was Galileo. The telescope, or what you and I would regard as a telescope, was invented a year or a little bit more before by the Dutch. Galileo knew of a design by a Dutch lens maker named Hans Lippershey and constructed his own based on accounts that he had heard. And while the telescope was really being used and thought about being used for applications on Earth, Galileo was really the first person who had the wherewithal to point it at some place other than the Earth. And in particular, he pointed it at the sky. Now, the telescope showed him many remarkable things. And if you've heard any stories about Galileo's early work with the telescope, you know what those things are. Phases of Venus and, the planets and the moons of Jupiter, blah, 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 blah. But what he really discovered, and the subject that we care about tonight, is the Milky Way. So this is a sketch of Galileo's picture of the Pleiades. Okay, so the seven sisters to the naked eye are seven stars, the seven stars of Subaru. But when he pointed the telescope to the Pleiades, what he discovered is he could see lots and lots and lots of stars that could not be seen with the naked eye. And as he panned around the rest of the Milky Way, he discovered that this was true no matter where he looked. Okay, and so what he wrote about the galaxy, so everything was published a year later in 1610 in a very famous book called Sidereus Nuncius. So this is Sidereus, a couple of pages from Sidereus Nuncius that have his observations of the Pleiades. Okay, what he said in Sidereus Nuncius, now it was written in Latin. You can still get it in Latin. I never took Latin, but people older than me, like my mom, took Latin in high school. But you can get English translations of it. And this is what he wrote, translated into English. He said, "The galaxy is nothing else than a congeries of innumerable stars distributed in clusters." Congeries is an old word that means jumbled. To whatever region of it you direct your spyglass, the telescope, an immense number of stars immediately offer themselves to view, of which very many appear rather large and very conspicuous, but the multitude of small ones is truly unfathomable. Okay, and I've added the emphasis there on the last bit because really Galileo stumbled on the most important thing about galaxies right here. The idea, the reality that galaxies that you and I perceive as smears of light in the Milky Way, which we perceive as a smear of light, is really the light from a nearly uncountable number of stars. Okay. Now Galileo at that time didn't have the equipment to start counting them, nor did he have the ability to count them. Even today, we have not counted every single star in the Milky Way. We estimate the total number of stars based on counting in a few directions by the mass of the Milky Way and other physical principles. Okay, and so the number, which Galileo here says truly unfathomable, you will see quoted between 100 and 400 billion stars in the Milky Way galaxy. Okay, so that was in 1610. Okay, this set off the beginning of the astronomy movement. It was confined largely originally to the gentry, people who could afford to have telescopes. Telescopes became very common at parties. They were drawing room attractions. You'd have people come over. You'd listen to music on the harpsichord. You'd eat pork chops and drink wine, and then you'd go out and you'd look through the telescope. Okay, and so discoveries began to be made, and there were all kinds of ways that people could make names for themselves in astronomy. Discovering comets was one of them. Discovering asteroids was another. But by and large, people began to discover all kinds of things. And it was very undirected, I would say. But there were points in people where they were trying to understand what the implications of what we could see through the telescope really was. And the first person to really think hard about the Milky Way was William and Carolyn Herschel. And so in 1784, so this is Herschel with one of his, must be his 10-inch telescope. Herschel and Carolyn decided they were going to map the Milky Way. Okay, so you could see the Milky Way up there, and so they were going to use the telescope to try and make a map of what the distribution of stars looked like so they could understand the shape and structure of the galaxy. Okay, and they used a method called star gauges. Now, the beauty of the internet, which you and I currently live in the world of the internet, is you can still get Herschel's Herschel's paper that he wrote about the star gauges and the mapping of the Milky Way. So it's in Philosophical Transactions of the Royal Society. There's the page number and volume. It was published in 1785, so the year after they decided to start doing this. Here's a picture of the survey, the description of the survey that the Herschels did to map out the Milky Way. So this is in their paper if you go get it from the Royal Society. Okay, so they're basically taking a cross section of the galaxy, and they're going to use observations in that cross section to reconstruct the map of the galaxy. Okay, now there are some assumptions that you have to make in order for this methodology called star gauges to actually work, okay? And the most important one down here is that Herschel had to make the assumption that the stars are uniformly distributed in the Milky Way, okay? And that his telescope could see all of them, that there weren't some that his telescope was going to miss. And so you can see that in the sketch that they're trying to make there is that big box which represents some observation that he's making. There's kind of an even smear of stars no matter where you are in the box. All the stars are kind of drawn the same size, indicating they're about the same brightness. Okay? So the assumption is often, and there's kind of debate about what star gauges actually means, but I'm going to tell you this because if you go look up star gauges on your own, this is usually the most common description of what star gauges meant. But if you go read Herschel's paper, and I've read Herschel's paper, I don't think this is quite it. But nonetheless, this is the kind of layperson explanation you'll see. Okay, and so the assumption that Herschel made is that he could see all the stars and that they were uniformly distributed. And the way that's often interpreted is that every star has the same intrinsic brightness. Okay, so you and I know when we go look at stars in the sky, some are bright and some are dim, right? So Sirius is very bright, but Polaris is not very bright. Okay, and there are two reasons for that. One reason is they're different distances away from each other. And the other reason is that intrinsically, the amount of light they put out is different. It's like the difference between a 100-watt light bulb and a 40-watt light bulb. Okay. Herschel's, or the description of Herschel's assumption for star gauges that I'm describing to you right now is assume all the stars have the same brightness, the way we think about light bulbs. Imagine they're both 100-watt light bulbs. So if the stars are at the same distance away, they will appear the same brightness. But if you then take one star and you move it farther away, or one star and move it closer, then one of them will appear brighter strictly because it's closer. Okay? And similarly, if you move it farther, if you move it farther away, I shouldn't look at that screen. I should look at this screen. If you move it farther away, then it will look dimmer than the one that is closer to you. And so if all the stars are the same brightness, then you can use the relative brightness of telescopes relative brightness of stars in the telescope to decide how far away they are. Bright ones are close and dim ones are far. Okay, so that's the basic translation that people have made of what Herschel was trying to do. So he did this with the famous 20-foot telescope. This is a baby telescope compared to the very famous 40-footer. In those days, telescopes were described by their focal length, not by their aperture. So the 20-foot telescope was a 19-inch diameter telescope, so not that dissimilar to some of the Dobbs that you and I get to use and may have. But the focal length is enormous compared to what you and I are used to. So that's like f10. Okay. And of course, parabolizing mirrors then is as hard as it was now. And so a nearly spherical mirror was necessary for the type of design that Herschel used. This is called a Herschelian. There's not actually a diagonal in a Herschelian reflector. You actually put the eyepiece right here on the lip of the telescope, and so the light goes into the telescope and it comes back up to the eyepiece right here on the lower edge. Okay, so you have a highly spherical mirror, and that kind of prevents aberrations. Okay, So this was it's kind of like a Dob though, right? It rotates in altitude and azimuth. And so Herschel would sit up here, he would stare through the eyepiece and count all the stars he could see in a given direction, and then he would call down to Caroline and she would record dutifully the number of stars and what brightnesses they actually were. And they did that 683 times, looking in every direction they could in the sky. Okay, and the outcome of that is Herschel's famous map of the Milky Way. You will see this reprinted often in astronomy textbooks and books about astronomical history. This is his picture of the map that he got. It looks not unlike a galaxy, right? It has some very notable features. It's large and flat. It has a big occlusion over here on the side that we know is the Great Rift in Cygnus, for those of you who are familiar with the Milky Way. And then there are other kind of exclusions where various other obscurations that we know exist in the Milky Way actually happen. What the Herschels wrote about the Milky Way was this. They said the Milky Way is a very extensive, branching compound congeries, that again, jumbles, of many millions of stars, right? So he was counting stars, so he said many millions of stars, which most probably owes its origin to many remarkably large, as well as pretty closely scattered small stars that may have drawn together the rest. And so here I have added the emphasis again at the end because this is just about 100 years after the publication of the Principia by Isaac Newton. Newton published the Principia in 1687, and what you see here is less than 100 years or so later, you already seeing people using the lessons that the Principia taught us, namely that gravity is a universal force that exists between objects with mass, stars in this case. And you see Herschel saying, oh, look, it must be gravity that's holding the galaxy together. Okay? Now, you'll notice a bright star right there in the center, very near the center, and that is Herschel's best guess as to where the location of the sun actually was. Okay? And we'll come back to the location of the sun in a minute. Now, if you ever get the chance to go to Chicago to the Adler Planetarium, on their telescope floor, you will see they have a rendition of Herschel's map. It's in this green acrylic, but what I like about this rendition is if you go see it, you can walk around it. And on the back side of it, they have the actual model of the galaxy where they've put stars down on the acrylic discs. And if you keep walking all the way around, you can see that's against a mirror. So you can see how the disc shape of the Milky Way actually leads to the map that Herschel actually made. Okay, so it's very cool. If you ever get a chance to go to the Adler, I highly recommend you go check it out. Okay, so that was the best anyone could do for nearly 120 years or so after that. Okay, and the reason that was the best anyone could do is because no one had yet solved what is the hardest problem in astronomy. Okay, and the hardest problem in astronomy then is still the hardest problem in astronomy today, and that is how to determine distances. In order to make an accurate map of anything in the universe, you have to first know how far away it is. And then its appearance in the telescope can be used to deduce what its properties actually are. Okay? So the hardest problem in astronomy has by and large been solved. We have methods of measuring distances all across the universe now. But up until the early 1900s, there was no way of measuring distances in the universe at all. Okay, so it was an unsolved problem until it was solved by this woman. Okay, so this was Henrietta Swan Leavitt. She was one of the Harvard computers who worked at the Harvard College Observatory. Those of you who know this history, the Harvard computers were a group of women, all of who had gone to college. They were well educated in science and math, and they were hired by Edward Pickering, who was the director of the Harvard College Observatory in the early 1900s. And the reason is they were technically skilled, but he could hire them for a fraction of the price that he could hire technically trained men. And so he hired this remarkable group of women who are responsible for all kinds of different things in astronomy. He paid them about 30 cents an hour, which is about $10.50 a week or so. And among them was Henrietta Swan Leavitt. She had a degree from Radcliffe College in astronomy. She was deaf. She had lost her hearing in her 30s due to an illness, which I can't remember right now. I want to say scarlet fever, but I don't know if that's right. But she worked at the Harvard College Observatory until her death in 1921. So she was 53 years old when she died. She died of stomach cancer. But during her time there in 1913, 1914 or so, she solved the problem of how to measure distances. And so I want to tell you what that is because it has bearing on our story tonight. So we're back to the problem that the Herschels had, which is you can't tell the difference between a star that's really close and dim or a star that's really bright but far away. They look the same in the telescope. They look the same to your naked eye. So when you look at the sky like this, the stars are clearly all different brightnesses, but you have no idea if some of them are super close or if some of them are super far away and why they look the way they do. Okay? So Leavitt solved this when she was working on a different problem. Okay, and this is very typical of the way discoveries happen in science. And it's very typical of the way scientists actually kind of stumble on things, right? Is you're solving one problem and you notice something that becomes useful in another application. And the people who really kind of change astronomy and change science have the wherewithal to realize that they see something no one else has noticed before, and then they can figure out what to do with it. And that was certainly Henrietta Swan Leavitt's case. So she was studying in those days variable stars. So these are stars whose brightness goes up and down over time. And there's a whole bunch of different kinds of them, but she was studying them. Pickering had given her the job of cataloging variables in the Magellanic Clouds. So we can't see the Magellanic Clouds from the Northern Hemisphere, but if you go to the Southern Hemisphere, or if you get the chance to go to like the Winter Star Party, you can certainly see it from the southern latitudes of the United States. Okay, so there's a so-called small Magellanic Cloud and a large Magellanic Cloud. So these are galaxies in and of their own right, but they are small. They're not giant galaxies like the Milky Way. They're what we call dwarf galaxies. And they're so small that they have gravity to keep themselves together, but they orbit the Milky Way the way a star orbits the Milky Way. Okay? So what Leavitt was doing is she was looking at stars in the Magellanic Clouds, and she had the following realization. She was looking at stars that were so far away. They were all, so the Magellanic Clouds are 50 kiloparsecs away. So that's 150,000 light years. Okay. She knew they were far away. She didn't know how far away they were, but she knew that they were really far away, and the galaxies themselves were small compared to the overall distance to them. Okay, so what that means is a star on the near side of the Large Magellanic Cloud is not that much closer to us than a star that's on the far side of the Magellanic Cloud. The way I describe that to people is say, imagine you're trying to tell someone how to get to a McDonald's in Denver. If there's a McDonald's on the close side of Denver and a McDonald's on the far side of Denver, you're not going to distinguish between those two because Denver's so far away from where you are right now. Okay, this is exactly the way Leavitt was thinking about the Magellanic Clouds. Okay, and so what that meant to her is that if she looked at stars only in the Magellanic Clouds, she absolutely could tell which ones were intrinsically bright and which ones were intrinsically dim. She could tell 40-watt light bulbs apart from 100-watt light bulbs because they're all basically the same distance away. Okay, so what she was discovered then is that if you look at these variable stars she was looking at, the ones that are brighter have different amounts of time that they spend getting brighter and dimmer. And the ones that are dimmer change as well, but on a different time scale. Okay? So these are a very special kind of variable star that we call Cepheid variables. And what that means is if you have a 100-watt Cepheid, compared to a 40-watt Cepheid, they get brighter and dimmer depending on what their intrinsic brightness is. 40-watt light bulbs take a certain number of days, and 100-watt light bulbs take a different number of days. Okay, and so what that means is all you have to do is know you're looking at a Cepheid, and you know absolutely what its true brightness is by simply timing how long it takes to get brighter or dimmer. Okay, so this is very famous. We call this Leavitt's Law, 1912. Sorry, it was a couple years late. 1912, she discovered this. Okay, and if you go read about this in astronomy books, it's called the Cepheid period luminosity relationship. So the period is the time it takes to get bright and dim. The luminosity is how bright it gets. Okay, so this is called Leavitt's Law, and instantly it allowed you to look at any Cepheid variable anywhere in the universe. You time how long it takes to get it bright and dim. That tells you is it a 40-watt light bulb or a 100-watt light bulb. You look in the telescope. You say, this is how bright it is. That means it's a 40-watt light bulb that is 10 light years away. Okay, that's kind of the way the reasoning goes. Okay, so this was a watershed moment in astronomy, and astronomers instantly realized that she had solved the puzzle. And so people began to use their telescopes all over to try and start measuring distances in the Milky Way. Okay, so the very first person to do this successfully, use Leavitt's Law, used the largest telescope in the world at that time. Okay, so that was the 100-inch Hooker telescope on Mount Wilson. It had just been completed in 1917, so this was 5 years after Leavitt made her discovery. Okay, and the person using it was a guy named Harlow Shapley. So Shapley was the director of the Mount Wilson Observatory. He's famous for many, many things. He made many contributions to astronomy, but the thing that most people remember him for is that he hired a very famous astronomer who will come into our story a little bit later, named Edwin Hubble. Okay, but Shapley was Hubble's boss, and when they built the telescope, Shapley was using the telescope. And what he was interested in was globular clusters. So you see a picture here of a globular cluster. So this is one of the globular clusters around the Milky Way. These are collections of stars that are the oldest stars we know of in the universe. Okay, so the Milky Way has something like 120, 150 of these globular clusters. They are about 500,000 to 1,000,000 stars each. They are so densely packed together that their gravity keeps them together in a ball shape. That's why we call them globular. Okay, and they're very red, like you see this one, because they are old, old, old stars. Okay, so Shapley was very interested in these, and this particular one is in the direction of Scorpius. There's lots of these you can see in your backyard telescope, as I'm sure most of you amateur astronomers know. And so he began looking for Cepheid variables in globular clusters, and he found them. Okay, and so the fact that he could find Cepheids means he could instantly apply Leavitt's Law to the Cepheids in the globular cluster, and thus measure the distance to the globular cluster. Okay, so this is a projection of Shapley's map of the globular clusters relative to the sun. Okay, and he got something that looked like this. Okay, now the globular clusters can be seen all around the Milky Way. If they're orbiting the Milky Way, you expect them to be randomly distributed in every direction around the Milky Way. But for a long, long time, even if you go all the way back to Herschel's map, people had thought the sun was close to the center of the Milky Way. And Shapley's like, well, that can't be true because the globular clusters are not centered on the sun. They should be centered on the Milky Way. And indeed, that is the first time we ever figured out where in the Milky Way the sun actually was. Okay, so the center of the globular clusters is about 8,000 parsecs, 24,000 light years or so away from the sun in the direction of the constellation Sagittarius. Okay, so this was the first time that we were ever able to reliably position the sun in the Milky Way. Okay, now as soon as that was done, other people got in on the game. Okay, so this is a part of astronomy that we call observational astronomy, using things you can see in the telescope to figure out what the universe was like. But then you come in and you do what we call theoretical astronomy or theoretical astrophysics, where you try and make models of what you see and you apply the laws of physics to get those models. And the first person to do that was a guy named Kapstein. So Kapteyn was very famous for building the very first theoretical model for what the shape of the Milky Way was, trying to get to what you and I today know is the kind of pancake spiral galaxy shape of the Milky Way. Now, a historical note, which is another story we can come back to someday. I'll give you another talk sometime if you want. This is called the Kapteyn universe. And what this is reflecting is something that at that time in astronomy was called the Great Debate. Okay, we were just now beginning to measure the distances in the universe, and people were arguing about whether or not the Milky Way was the entire universe or whether or not there were things beyond the Milky Way. Okay, the argument was made that everything you could see in the telescope was actually inside the Milky Way because the Milky Way was the whole universe. Okay, so Kapteyn's model of the Milky Way is usually called the Kapteyn universe. Okay, and so you can see here, this is the abstract of the paper. You can still get all of these papers online. It's called The First Attempt at a Theory of the Arrangement and Motion of the Sidereal System. Sidereal means stars here. Okay, so what he ended up with, his map, is not the Milky Way as you and I know it, but it's a pretty good mathematical approximation that you could get from the star counts at the time. Okay, so he modeled the Milky Way as a flattened ellipsoid of revolution. So you and I think of the Milky Way as a disk, but an ellipsoid is like a football that you've tried to squish down flat. He estimated, based on the number of stars that had been counted, there are some 47 billion stars in the Milky Way, so that's maybe a factor of 10 less than we actually think there are. It has a radius of about 8,500 parsecs, a thickness of about 3,000 parsecs, and the sun is 650 parsecs from the center. Okay, so those numbers are not perfect. Okay, and the reason was he was working from the best data they had at the time, which was not great. They were doing a new star count survey at Mount Wilson with the Hooker telescope, but it wasn't done yet. And there were things that he didn't know about the Milky Way that you and I know today. Most importantly, that there's dust in the Milky Way, and so we can't always see all the stars through the dust in the galaxy. That's what the Great Rift in Cygnus is actually doing. It's blocking the view of the far side of the Milky Way. But I love Kapteyn's paper, and it's worth reading. This is an excerpt from it that I like, and let me read it to you. It says, "My aim in the present paper is simply to get hold of some approximate information about the real structure and motion of the system, and quantitative accuracy has been considered of secondary importance, as long as we may hope that the main features are not affected. I hope that this hope will not be disappointed, notwithstanding the many defects that will be duly pointed out, which still attach to the present treatment." Okay, so this entire paper and Kapteyn's attitude, which he presents here, is really a masterclass in how scientific understanding really works, and especially how our understanding in astronomy works. We are never going to have perfect understanding of what the universe is like because we are flat-footed here on Earth, looking out through the universe from our viewpoint here. We're never going to be able to go out there. We're never going to see everything. We're not going to be able to look at it from different directions. We're never going to be able to bring pieces of it back and work in the lab. We have to learn everything that we know from here on Earth. Okay, and so our knowledge is always going to be imperfect. And one of the things we do very well as astronomers is exactly what you see Kapteyn doing here, is acknowledge that there's stuff we don't know, but this is the best we can currently do. And as our knowledge improves, the defects will duly be pointed out, then we'll update our understanding of the universe. Okay, and so this gets considerably better over time. Certainly the biggest mystery that Kapteyn didn't know about is the existence of dark matter. And it's only today, in my and your lifetime, that we've really gotten to the point where we understand that dark matter is there and understand how it influences the galaxy. But that's another story for another day. Okay, now, this was all a big kerfuffle for a long time. As I said, this is Kapteyn's universe. The Milky Way was the only galaxy that we knew about at that time. There were other galaxies that we could see in telescopes, but we didn't know they were galaxies. They were in fact called nebulae. Okay, there was a mystery surrounding them because there were some galaxies, some nebulae that we called the spiral nebulae that were a little weird. Okay, but it wasn't until 2 years after Kaptein's paper that we finally solved the mystery. Okay, and so that breakthrough was made by that young astronomer that Shapley hired at Mount Wilson, Edwin Hubble. Edwin Hubble was looking for variable stars in the spiral nebulae. And so this is a very famous picture he took. This is plate H335H, which is owned by the Carnegie Observatories. Okay, Carnegie Observatories in Pasadena. And you'll see here, he took this in October. And what he would do is he would take pictures on these 4-inch by 5-inch glass plates. Okay, and then he would go back and compare the same pictures over and over again to see if things change. Okay, and so he thought, you can see up there near the top, there's these little hash marks with an N next to it. He thought he had discovered a nova in the Andromeda galaxy. Okay, and then you see crossed out in red, the N is crossed off and it's written VAR. Okay, and that's because he had gone back to another plate and discovered that, in fact, that star, which he thought was a nova, a one-time event, actually was changing brightness with a measurable period of about 31.4 days. This was the very first star ever discovered in another galaxy, and in fact, it was the very first Cepheid discovered in another galaxy, which immediately meant that Hubble could take that Cepheid variable, apply Leavitt's law to it, and determine the distance to the Andromeda Nebula. And he got that the distance to the Andromeda Nebula was 900,000 light years. This was far and away the most distant object that had ever been measured in astronomy at that time. And astronomers believed and knew the Leavitt's law, and so this was incontrovertible evidence that the universe was far larger than the Milky Way, which at that time we knew was only about 100,000 light years across. Okay, so this is kind of an amazing thing to think about, and I'll have some recommended reading for you at the end. It's like astronomy literally had to change what we thought and understood about the universe overnight, and it's all because of this one discovery. Okay, now that number there, that 900,000 light years, is about half the current known value. That has to do with the calibration of Leavitt's law, which has gotten better over time. So the true distance of the Andromeda galaxy is about 2 million light years. So the reason this is important to our story, we could talk about the discovery of galaxies in the universe, but the reason this is important to our story is because now it allows us to see all of those spiral nebulae, not as nebulae, but as examples of what galaxies can look like. Okay, and if we're trying to understand the Milky Way, which you and I will never be able to travel completely across or see from any other different view, then one of the ways that we understand what the shape and structure of the Milky Way is something that we call comparative galactic morphology. We look at other galaxies and we say, look, these are the properties of galaxies that are common. All of the spiral galaxies have these properties, all of the elliptical galaxies have these properties, and so on. And so by looking at many, many examples of spiral galaxies and comparing it to what the Milky Way looks like, we can say things like, the Milky Way must be similar to other galaxies in the following way, therefore we are probably of this type. Okay, and so that's one of the ways that we do it. Another way that we've done it in modern astronomy, and this is just in the last 100 years, is that we have learned that we can look at the galaxy in different kinds of light. Okay, so up until the early 1900s, all astronomy was done in optical, this band right here across the lower portion here. This is what the Milky Way looks like through your telescope and to your naked eye and in photographs. But one of the things we've discovered in astronomy is that all the other kinds of light, infrared light, radio light, X-rays, gamma rays, are all useful for understanding the physics of what's going on stretched across the galaxy. And so these are the way the Milky Way looks in all of these different colors of light. And what we've discovered is that it reveals not just the structure of the Milky Way, but what the composition of the Milky Way is. All of these different kinds of light are created by different physical processes. And so that allows us to understand what the kind of remote areas in the Milky Way are like, even though we're never able to go out and get a test tube of whatever's out there. Okay? Now, this is kind of what we've done for the last 100 years or so, but just in the last decade, there's been a new mission to take up the Herschel's original goal of mapping the Milky Way. And that mission was called Gaia. Gaia just shut down several months ago, I think. But the Gaia data is online, and professional astronomers can get it, but so can all y'all, right? And you see lots of people downloading Gaia data and playing with Gaia data. They have neat tutorials and tools. If you know how to do Python and stuff, you can certainly play with it. But what did Gaia do? Gaia measured the distance to 2.1 billion different stars in the Milky Way. Okay, so this is a rendition of what the Gaia map looks like. You see the sun is down here in this very bright spot, and you can see the lines going out from the sun in every different direction. Okay, and the places where it's kind of purplish is where we have fewer and fewer stars, and down here where it's very bright is where we have lots and lots of stars. But the extent of where Gaia has measured stars goes all across the entire Milky Way. Okay, now this kind of looks like that photograph of the Milky Way that I showed you at the very beginning. But this, in fact, is not a photograph. This is a computer-generated image where they've taken the brightness and the distance and the color of each star measured in the Gaia database and simply plotted it on the screen. And what's remarkable is it looks exactly like a freaking photograph, right? I love this. Okay, so this is a computer-generated rendition of the Gaia database, just using the information in the database. And it looks exactly like what you and I expect when we go out and stare at the Milky Way in the night sky. Okay, so the story we have then is the Milky Way is 100,000 light years across. That's 588 quadrillion miles, for those of you who like miles better. The sun lives about 2/3 of the way out from the center. There's still much galaxy beyond us. We live in a part of the galaxy called the Carina Cygnus arm. Okay, and all of these stars, and in fact, this spiral structure is orbiting the center of the Milky Way. And so, kind of an interesting thing to think about is the fact that the sun orbits around the Milky Way once every 250 million years. Okay, so that means in the context of the sun's life, right, it's gone around the sun only, or sorry, it's gone around the galaxy only 18 times. Okay, the Milky Way is old, but the sun is still a teenager. It's only had 18 orbits of the center of the Milky Way. Okay, but each of those orbits is 250 million years long, which is enormous compared to a human lifetime. The last time the sun was where it is in the current place in the galaxy, right, it was 250 million years ago. That was during the Triassic period, for those of you who are geology nerds, right? And that was when Pangaea was still a supercontinent, and the first dinosaurs were only beginning to emerge. As the sun goes around in its orbit 200 million years ago, it was not quite of a quarter of way along the orbit. That's when stegosauruses appeared. Okay. 150 million years ago, not quite 180 degrees around the orbit, maybe 120 degrees around the orbit. That was the first time giant sequoias appeared on the planet. 130 million years ago, on almost straight across the orbit from where we are now, on the far side of the galaxy, that was the first time flowers appeared. 100 million years ago was the Cretaceous. There were Triceratops and Velociraptors for all you Jurassic Park fans. Okay. And it wasn't until 65 million years ago when we had Tyrannosauruses. Okay. And 65 million years ago is important in the history of the Earth, because that was when the KT extinction happened. That's when the asteroid hit the Earth and left the iridium layer. That's the evidence for the asteroid impact on Earth. You can go see that. So you're all there in Kansas. So if you make a quick jaunt over to Trinidad State Park in Colorado, Colorado. There's a trail there at Trinidad State Park called the Dinosaur Walk, I think, something like that. But if you walk along it, there's this little hillside that's kind of been cut away by the rain and the weather, and you can see right there in the hillside the iridium layer. Okay, and that's my pocket knife there next to it to give you a sense of the size. It's very small, but it's very visible. Below that layer, you see dinosaurs. Above that layer, you don't see dinosaurs, and so that's how we know this extinction event happened from that asteroid impact. Modern humans only appeared on Earth about 500,000 years ago, so we have not seen the far side of the galaxy, even though our dinosaur friends lived over much of the last orbit of the sun around the galaxy. Okay, so we have just a few minutes left, so let me tell you a few things about modern theoretical work on the Milky Way, because this kind of leads to what my group does. And this is basically about studying the Milky Way on computers. Okay, so my favorite story to tell people about studying the Milky Way on computers is the very first numerical simulation of a galaxy. It was done in 1941 by Eric Holmberg in Sweden. Okay, and so computers didn't exist in 1941. This was just the beginning of World War I. Some of you know the history of computers will famously know that the very first computers were built for cryptography in 1941. But nonetheless, Holmberg did a numerical calculation of the shape of a galaxy in 1941. And the way he did that is he built little robots that had light bulbs on them and light sensors on them. Okay, and the idea is that light declines in strength in exactly the same mathematical format that gravity does over distance. So we call this the 1 over r squared law in physics. And so what he did is he set up all these robots in basically these circular patterns here. He turned on their light bulbs, and then he turned on their sensors. And basically what the sensors did is it measured all the light it could get from the robots around it, like all the light from the stars around it, and then it moved in response to those as if it was experiencing a gravitational force. Okay, and so you turn it on, it sees the light, it says, oh, there's a whole bunch of bright stars here and a whole bunch of dim ones here, so the gravity feels stronger in this direction, so the robot moves in that direction. Okay, and the outcome of that is that if you let the robots run over time, then they form spiral arms, and they look just like galaxies. Okay, so this is my big goal in life, is to get a whole bunch of Lego Mindstorms robots and set this up in a high school gym and do a Holmberg simulation again to show that you get these kinds of structures. Okay, so modern computers, of course, do this properly. They're called n-body simulations. We put all the stars in the computer, we calculate the Newtonian gravity, and then we just move them forward in time. And then the other thing that we do is called population synthesis. This is where we put all the physics about how stars are born, how they live their lives. We simulate their whole lives from start to end, and then we use that to tell you what the galaxy should look like. And it's this part here at the bottom that my group actually works on. Okay? So the reason we do this, and you heard Rick say this at the beginning, is I work in something called gravitational wave astronomy. So LISA is a gravitational wave observatory in space. It will consist of 3 individual spacecraft. They'll be launched in about 10 years. They shine lasers back and forth between each other because when the gravity from distant gravitational systems passes over them, it stretches and shrinks these arms a little bit, which we can measure with laser light. Okay, and I have a whole gravitational wave talk I can give you sometime if you want to know about that. Okay, so the distance between each of these 2 spacecraft is 2.5 million kilometers. So it takes light 8.5 seconds to fly from one spacecraft to the other. And the whole constellation will be in the Earth's orbit behind the Earth. So as the Earth goes around the sun, LISA's just going to follow it around the sun. Okay? There are all kinds of things we're going to see with LISA, but in particular, one of the things we're going to see are the stellar graveyard of the Milky Way. When stars like the sun die, they become something called white dwarfs. Something you may have been told is that 50% of all the stars in the sky are in binaries. And something you may have also been told is most stars are ordinary stars, kind of like the sun, which means most stars, when they die, are going to end up with 2 stellar skeletons, which we call white dwarfs orbiting around each other. Those emit gravitational waves. We call them the ultra-compact binaries. Okay, and the collection of them in the Milky Way we call the binary stellar graveyard. And there are between 10 and 100 million of them in the Milky Way, which means they are going to be the most prolific source of gravitational waves that you have ever heard about. All the stuff you've read about LIGO or heard about gravitational waves, LISA is going to just dump tons and tons of sources into the catalog. And lots of them, these white dwarfs in particular, are going to be multi-messenger sources, which means people like me and you, amateurs, can see them in our telescopes in the backyard. And in fact, many of the archetypes for this, we know about them because the amateurs have monitored them and determined their orbits that we actually use in our professional work. Okay? So my group simulates these, and these are two models of our Milky Way galaxy. There's a lot about the Milky Way that we still don't know. In particular, we don't know how fat it is. Okay, and so here's a thin model and a fat model. This has to do with the total stellar population in the center of the Milky Way, what we call the bulge. And you can see that they're quite different. And so this is one of the things that LISA will be able to tell us, because these two movies represent the stars that LISA can measure, and you can absolutely tell the difference between these two. This is a simulation flying out from the sun through the Milky Way, and as it zooms out, you'll see stars appear. So these represent all of the stars that are visible to LISA. Some of them are purple and some of them are red. The purple ones are the ones that can be seen with both LISA and telescopes, and the red ones are the ones that can only be seen by LISA. Okay, and so what you see is LISA will map out the whole galaxy, but for the ones that are close to us, and these black dots that you see here, these are several of the ones that we already know about that we can see in telescopes. These purple ones here around the sun are the ones that we'll be able to see. Okay, so, whoops, I just went backwards. What did I just do? Okay, so this is all I wanted to tell you. Really, the most important thing is probably the most important lesson that anyone can really know or learn about astronomy or science, which is our understanding of anything in science, and in particular, our understanding of the Milky Way, changes with time. And it really changes with our ability to enhance or develop our observations, which is very often driven by technology. In our case, it's been driven by bigger and better telescopes and by new technology like LISA or LIGO. What we decide to work on is really based on what we think the current mysteries about the galaxy are. Originally, this was how do we determine distances. It went to Shapley's, where are the globular clusters? It changed into what are the spiral nebulae, which are other galaxies. We still have lots and lots of questions. All of these sorts of things, which are all mysteries that we still don't understand, but which we're slowly uncovering as we build better technology and better observations. Okay. And so the most important thing, particularly for those of you who are thinking about like careers in astronomy because you haven't gone to college yet, or those of you who are thinking about careers in astronomy because you're tired of being a dentist or a taxi driver or whatever you are, you're going to go back to school, right? Is that there are things that are going to be discovered in your lifetime, even if you're not an astronomer, that we haven't even thought of yet. Okay. And that's what happens when you build new telescopes and new technology. It happens all the time. Okay, so a few things for you to read. I always lead you with a few recommendations. So these books over here are both about the Milky Way. They're about the structure of the Milky Way, the kind of stuff that you and I have been talking about, how we learned about it and figured it out. This is the only biography that I know of written about Henrietta Swan Leavitt. She famously didn't keep diaries. There's not been a lot written about her. And so George Johnson wrote this really spectacular little book called Miss Leavitt Stars, and it's about Leavitt and her education and her discovery of Leavitt's law. If you're interested in the Harvard computers, this book by David Sobel, which some of you may have read, is an excellent one. It's called The Glass Universe. It's about the lives of all of these women. So you may know their names: Wilhelmina Fleming, Annie Jump Cannon, Henrietta Swan Leavitt. All of them were Harvard computers, and so this is a really great book. I meant to put on here Hubble's book, the book about Hubble's discovery. There's a great book by Marcia Bartusiak called The Day We Discovered the Universe, and that's about Hubble's measurements to the galaxies. So, For those of you who like to tinker, this is the book that I recommend for those of you who like computing. Some of you may remember Sky and Telescope used to have an old a column called Astronomical Computing. And so this is a book that's about a lot of that. And I really like this book. It's about 12 or 15 different projects, shape of a comet's tail. There's a spiral galaxy one. There's a structure of a star, all kinds of stuff in there. But it kind of teaches you a little bit physics, teaches you some numerical methods, and then it gives you all the codes in basic format. And I've Googled them. If you're a Python programmer, there's someone has a GitHub where they've converted it all to Python, so you can certainly do it there as well. Okay, so that's all I'm going to say. I'll certainly say thank you for your time. I'm happy to take questions, but I will pass it back to Rick, and we'll do what he says we should do.
Well, thank you. I built you up with everybody in the club about what a great you were. So thanks for following through.
Okay, well, I do my best. So, are there questions? Oh, I see folks on camera here. Let me stop sharing. I'll share again if we have questions about the slide, but I see there's some of you on camera. So, questions?
One question.
Sure.
In your work with gravitational waves,
Mhm.
that kept Thorne.
Yeah, so I was actually a postdoc in Kip's group when I was at Caltech. So I did my PhD at Montana State. I did my first postdoc at JPL at the Jet Propulsion Laboratory, and then my second postdoc was at Caltech. And I was with a guy named Tom Prince who works on this kind of binary star stuff that I do. But he was chief scientist of JPL when I was at Caltech. So I actually sat with Kip's group for the 3 years I was at Caltech. So. Yeah.
Cool. I read when I was in college in the late 90s, his
Yeah.
Black Holes and Time Warps.
Black Holes and Time Warps is the book I recommend everyone read if they like this stuff. Yeah.
He's talking about building
Yeah.
the stuff to do detect the waves. Now in the last 10 years, they've actually done it. It's pretty cool.
Yeah. So if you ever get a chance to go to Caltech, so at the time Kip wrote that book, so LIGO is 4 kilometers long. Okay, so there's one in Hanford, Washington, and there's one in Livingston, Louisiana. They both have visitor centers, so if you're ever in the area, you should stop and see them. But at Caltech, they built a 40-meter prototype. So this was basically to scale exactly what we built at Hanford and Livingston. And so at the time Kip wrote that book, the 40-meter prototype was what they had at Caltech. When I was a postdoc, which was a few years after he wrote that book, was when they were first building them on the actual sites. So yeah. So it's cool. Yeah, and in 2015 we just had the 10th anniversary of the discovery. So it's been a fun year because we've all been reliving that big discovery moment. So
So Shane, I assume that one of the advantages of the gravitational wave detection is that you can, it's not blocked. In other words,
mhm.
Normally we can't see through our galaxy.
Yep.
So that sounds like an advantage that those waves not.
Yeah, gravitational matter is transparent to gravitational waves. Okay, this is partly why they're so hard to detect because they kind of fly through your detectors and they don't make many changes. They're easy to measure. So they propagate through all the obscuring dust of the galaxy. They propagate through all the stars. They propagate through everything, and so they don't get impeded the way light does. So that's definitely an advantage. The disadvantage is this is why they're really hard to detect. And so, the idea for gravitational waves Einstein put forward in 1917. Okay. It took us until 1957 to figure out even how to build an experiment to detect them. And it took until the early 2000s to make one of those experiments happen. Okay, so that's just an extremely long timeline for experimental physics and really is indicative of how hard the technology is. But you and I live in the future and we've managed to build the technology. And so now we can use it as a tool, just like anyone who's built a telescope uses a tool to study the universe. So, and it has distinct advantages, one of which is the universe is transparent in gravitational waves.
All right. Well,
Okay.
thank you very much, Shane.
Okay. Rock and roll.
We
Well,
will.
thank you for your time, Rick. Thanks for the invitation. Yeah.
We will take you up on your offer of doing another presentation.
We'll do it again sometime. Yeah, it'll be fun.
All right.
Okay. Hopefully on night when the Chiefs aren't playing.
Yes.
Okay. Good luck, Chiefs. Okay.
All right.
Okay.
Thank you.
Take care, everybody.
All right.
Bye-bye.
Bye.